Hello, here we're going to look at 1.2, solving linear inequalities. Here's the why. Josh is trying to decide between two data plans offered by a wireless telephone company. To compare these two rates, we can use inequalities. So, you can see data there, that we're not going to go specifically into because the problem's not designed that well. But what it allows us to do is to compare. Inequalities allow us to compare. That's their key purpose. When we are looking at equations tell us where two things are perfectly equal. But as you all know, the majority of things in our world don't have to be exactly equal, right? To be on time to class, right, you just have to be there before the bell, right? So we don't have a bunch of students gathered around the door waiting to enter into the room exactly when the bell rings, because it's not an equation. Inequalities allow us to take care of things that can have a less than or greater than component. There are essentially way more useful equations, and the good news is that they operate just like equations, except for a few small differences. So another example of inequalities is paying. In most situations, you don't have to have exact cash or exact change, right? Exact change would be an equation. Instead, we have an inequality to where your dollar amount, right? So let's just say your wallet or maybe your debit card in there, as long as you are greater than or equal to the cost of something, you are able to purchase it, right? In order to beat a team in basketball, right, your score must be greater than theirs. Otherwise, you go into overtime, right? And we're going to cover some of the details about when there's a line underneath and when there's not. That's one of the special things about inequalities, that it allows us to talk about the exact spot of where things are happening to see if we can in fact be equal, or, as in for basketball or football or a lot of major sports, your score must be straight up larger than their score. So inequalities are all around us. Another example is a curfew, right? So if you have to be home before a certain time, right, you must arrive, before, right? So your time must be less than 8 o'clock. All right, if you had an 8 o'clock curfew, the time that you arrive better be 7:59 or anything smaller. All right, so inequalities are very applicable to our lives. We use them for almost any time you use an equation. It's actually most likely an inequality if you think about it. So let's talk about some of the vocabulary that goes into this. These symbols, so this one that faces to the open to the left is called greater than. This one is less than. Now, it helps to have this terminology instead of just saying a alligator's mouth opening left or the inequality opening right. If you can get this vocabulary down, you'll sound much more intelligent as you discuss inequalities and read them aloud. Right? That first symbol is greater than. The second symbol is less than. I remember that, or I tell people that, because it almost looks like an L, and that L stands for less than. So for this one is also greater than, but that line underneath denotes an or equal to. So that says you're allowed to be equal. So this one's going to have an or equal to as well. And this one is the less than. So the line underneath it does have important implications. One example of that would be on your curfew. If you are supposed to arrive before 8 p.m. and you show up at 8 p.m., 8 p.m. is not less than 8 p.m., you're in trouble, right? Or maybe they say that your curfew is you have to arrive by 8. If they say by 8, that would then put a line underneath the inequality, and then your 8 o'clock is less than or equal to 8 o'clock, no trouble. So the line underneath the inequality helps dictate the exact moment, right? It basically talks about what happens if there's a tie. So for basketball, we're not going to have a line underneath it because your score must be greater than theirs. If you have the greater than or equal to, that means you could potentially be going into overtime, and that's not what you want. So the line underneath the inequality essentially determines what happens if there's a tie. Is the tie allowed or not? So this is something here called set builder notation. We won't be using it in our course this year, but it is something that you'll see in the future. We're going to use just this part of inequalities, right? We will use our answers like this, to where this says b is less than -6. The set builder's notation is something more so you'll see later on in mathematics. And all it states is whatever variable you're discussing, so it's saying, hey, we're going to be looking at variable b, such that, and then we have the part that we'll actually be using, and it says b in this case is less than -6. The reason we won't really be using the set builder notation is because we won't be covering problems that use multiple variables to the extent of which you will in other courses, so we don't need to specifically state what variable we're talking about. We'll just use this part right here to express our answer. As for making a graph of this situation, that is one thing that makes inequalities special. So to graph b is less than -6, we're going to first go to -6, and I'm going to put a circle on -6. But notice that it's going to be an open circle. That's because if we're using greater than or less than, both of these graph with open circles. Both of these graph with open circles. Now, what that means is if there's a line underneath your inequality, you would graph with a closed circle for these two. Since we have no line under our inequality, we have an open circle, and what we're tasked with doing is shading, because b is less than -6, there are a lot of numbers less than -6. So we need to show those on the graph. And all of the numbers that are less than -6 will be in this direction. Now, I do want to mention, because a lot of times students will say, Mr. Cottle, I always graph whichever direction my inequality is facing. So we did just graph here, b is less than -6. People will say, Mr. Cottle, this is pointing to the left, so I shade to the left. That is not something that you can use, because if I use this property of symmetry, and I say that -6 is greater than b, these two things are the exact same. Notice that b, in this case, is less than -6. If I flip it around and say -6 is greater than b, this is the exact same answer, but now notice that your arrow, if you think of it like that, is pointing to the right, which would not work for our graph. So does the trick work if your variable's on the left? Yes, if your variable's on the left, you can shade whichever way it's pointing, but that's not a rule permanently because of situations like this, where your variable could be on the right. Instead, an easy way to double check if your answer is correct or not is to pick a number and see if it works, right? I'm going to pick a number from my shaded region. I'm going to pick -10. Is -10 less than -6? Yes. I know I shaded in the right direction. Notice what happens, though, if I pick a number that is not in the shaded direction, like 4. If I try to put 4 in for b, I'll say, ooh, 4 is not less than negative 6. That means I should not be shading in the direction of the 4. That's another tool that you can use to make sure that you are shading in the correct direction. So here we're going to look at the similarities and differences between solving an equation and solving an inequality. The similarity. Equality on both sides. What you do on one side, you must also do on the other. That concept of solving an equation is the exact same. Isolating the variable to where the ultimate goal is you get the variable by itself is also similar. Now, for the differences, one difference is the way that you express your final answer. Right? Your final answer now must be graphed. And I say must, sometimes we'll just leave it as the inequality, but to see a picture of it, the final answer can be graphed to view on a number line. And then also another difference is when you multiply or divide by -1. That causes something interesting to happen, right? And if you guys recall, if you multiply or divide by -1, you must flip the inequality. And here is why, and we don't even have to toss in a variable to understand why. If I say 5 is greater than -2, right? 5 is greater than -2. But if I go ahead and I introduce multiplication of -1 on both sides, and that is valid because what I did on one side I did to the other, I now get -5 and +2. So when you introduce a negative, it essentially flip-flops the two sides to where this inequality would no longer work, right? Because -5 is not greater than 2. So whenever you multiply both sides or divide both sides by -1, it swaps which side is larger, so your inequality must flip to accommodate that. Right? And that's a simple mathematical explanation behind why, when you multiply or divide by a negative number, that you must flip. Now, a question I'll get asked sometimes is if I give an inequality like this, when I go to distribute here, I am distributing a -3. So people will say, Mr. Carlo, you multiplied by a negative number. You need to flip that inequality. If you're just distributing or using some of the negatives that they had already inserted into the problem, you don't flip. You only flip on maybe a scenario where you get down to something like this, to where you personally introduce a new negative sign. That would be an example to where I must flip that inequality.